Hello and welcome to Chapter 8, Trigonometry, right triangle trigonometry. Now, in this particular lesson, we're actually going to skip 8.1, we're going to go into 8.2, and we're going to talk about, the Pythagorean theorem and Pythagorean triples. So, the Pythagorean theorem is something we've already talked about. We've used it throughout the year, and this is where it's going to be probably used the most, or most regularly. So Pythagorean theorem and triples. So Pythagorean triples is something that we will learn, or we're going to learn today. It's a very, very unique version of the Pythagorean theorem. And you'll find out what that does in just a second. So the Pythagorean theorem, as we know, is used for right triangles. Specifically the side lengths. Okay, and when we have the Pythagorean theorem, we use this formula. A squared plus b squared is equal to c squared, where c is the hypotenuse. C is the hypotenuse. Okay, and we should already know that. But in case you forgot, that's what it is. And let's draw a really quick right triangle. Nope, that's not going to do it. Again, that's interesting. There you go. We have a right angle here in the bottom left. We have C as your hypotenuse. And then we just have A and B, which are our legs. So let's call this just leg 1, leg 2. This doesn't quite matter which one you label leg 1, leg 2. It's all going to be the same when it comes to these when it comes to the Pythagorean theorem. So, for example, if we have values, let's say A is equal to 3 and B is equal to 4. We could use the Pythagorean theorem here to solve for C, the hypotenuse. And in this case, we have 3 squared, so let's say C is equal to, we don't know, 3 squared plus 4 squared is equal to C squared, okay? And 3 squared we know is 9, 4 squared is equal to 16, and C squared is equal to just C squared because it's just C squared. So 9 and 16 add up to 25, which is equal to C squared. And in order to get C by itself, we need to square root both sides. And fortunately for us, 25 is a perfect square, so we could actually perfectly square root this. And since this is an equation, we would say this breaks down to plus or minus 5 is equal to C. Now, in normal algebra, this is what we would do. But if we actually plugged in the negative 5 into the triangle, we know that there's no such thing as having a length of negative 5. So in these particular problems, we actually just ignore that negative altogether, right? And we just say C is equal to 5, okay? So C is equal to 5 here. Let me erase that. And we have a nice convenient values for A, B, and C, 3, 4, 5. And this is actually what we call a Pythagorean triple. So a Pythagorean triple, let's go ahead and write that first one down, Pythagorean triple. And I'm going to put underneath this, I'm going to put 3-4-5, where 5 is the hypotenuse, because it's the longest side. But a Pythagorean triple is a set of, how would I say this? A set of side lengths. Where A, B, and C are whole numbers or whole values and satisfy the Pythagorean theorem. So like I said, 3, 4, 5 is a Pythagorean triple because when we saw it here, they're all whole numbers and it satisfies this equation. Okay. Another Pythagorean triple is 5, 12, and 13. This is another common one. Okay. And if you do the math really quick for this, let's do it in pink so you don't have to copy this down. 5 squared plus 12 squared is equal to 13 squared. 13 is your C because it is the longest side. 5 squared is 25. 12 squared is 144. And then 13 squared is equal to 169. And we see here 169, 25 and 144 make that 169. 169 is equal to 169, so it checks out. It does satisfy the Pythagorean theorem, making this a Pythagorean triple. Okay? So, with that said, there are a number of Pythagorean triples. This list actually goes on infinitely. But what are the most common ones? Which ones are you going to see relatively frequently? Well, definitely 3, 4, 5 is the most common one. 5, 12, 13 is probably the second most. And 7, 24, 25 is another common one. Okay? Just for the sake of it, fill out these other two. 8, 15, 17, it's less common, but you might see it on occasion. And then 9, 40, 41. Okay, these are probably the 5 most that you'll ever see. But I do want to address this. Multiples of, let's take this 3, 4, 5 for example. 3, 4, 5 is our most common Pythagorean triple. But you could also take multiples of these and satisfy this, satisfy the Pythagorean triple definition. So for instance, if I multiply all of these numbers by 2, okay, and let's put that 2 in pink for now. I'm going to put this in pink. If I multiply that by, or I meant to put that in by pink too, then all the values in this Pythagorean triple is now going to be 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10. And if we check the math on this, what is 6 squared plus 8 squared? That is going to be 36 plus 64, which is equal to 100. And we know 10 squared is actually also equal to 100. So is this a Pythagorean triple also? Absolutely. And we could actually do this for any multiple of any multiple. So for instance, if we multiply this by 3, instead of 2, we're going to use a 3 here. Let's do this in pink. Let's just write a 3 here. We could also get another Pythagorean triple. It would be 3 times 3 is 9, 4 times 3 is 12, and then 5 times 3 is 15. This will also work as a Pythagorean triple, meaning we could use these base as a foundation for Pythagorean triples. We could just have a multiplier of n. N could be any whole number to keep it a triple. Okay, so if you multiply by 5, which would be 15, 20, and 25, that is still a Pythagorean triple. Okay, but what I also want to kind of address is this. This is going to be a little bit strange. You could also technically, so these are all Pythagorean triples, right? They all check out because they're all whole numbers. But what happens if you take this 3, 4, 5, and instead of doing a multiplier of a whole number, what if I multiply this by, what if I divided this by 3 instead? Okay, now our values are actually not going to be whole numbers anymore. Our value is going to be what's 3 divided by 3? 1. 4 divided by 3? 4/3. And then 5 divided by 3 is 5/3. Okay, this is no longer a Pythagorean triple because they are not whole numbers. However, would this still satisfy the Pythagorean theorem? 1 squared plus 4/3 squared is equal to 5/3 squared. Let's find out. 1 squared we know is 1. 4/3 squared, if you remember your properties for exponents, you have to distribute it into both. So this is plus 16/9 is equal to 5 squared and over 3 squared, which is 25/9. And then if we want to, we could just take this and we could say 9/9 because we know 9/9 is 1. And then just do some quick math. They all have the same denominator. We get 9/9 plus 16/9, which is 25/9, is equal to 25/9. So, to prove a point, even though this is no longer a Pythagorean triple, it still satisfies the Pythagorean theorem. Okay? And you could use that as a kind of, this is why I call it a foundation for Pythagorean values. Because you could use it as, doesn't have to be whole numbers to satisfy the Pythagorean theorem. It just needs to be whole numbers to satisfy a triple. Okay? So, with that said, you could do that with pretty much any of these values, whether it's a whole number, you multiply by a whole number, or you divide by a value or n value. You could get Pythagorean values out of some of these bases or some of these triples. Okay? Other than that, if you have any questions, this is the end of our lesson. Pythagorean theorems, Pythagorean triples. Please get in the habit, especially at the very least, knowing these three and recognizing we could do multiples of them. Okay? All right. Like I said, if you have any questions, please let me know, and I'll see you in the next one.